Alrighty, today's lesson is going to be like this, a video, and luckily the topic is not going to be that simple. Today's topic is going to be about Gibbs energy and equilibrium constant. Those two beautiful things, they will be combined, and let's see what kind of hideous monstrosity we get out from it. So the first part of this lesson is from topic reactivity 1.4.4, and the main idea, I'm going to use like 30 minutes to explain to you that whenever you see a curve like this, where there is Gibbs energy in the y-axis, you just need to know that this is the sweet spot, this is where the equilibrium lies. But after that, we start using this really nice and simple looking formula. So that is the goal of these two, this lesson. Okay, so let's see. Equilibrium and Gibbs energy, how they are connected. First, we start with, microscopic level, and then we start doing those calculations. Alrighty, so what we learned before was that if the Gibbs energy change is negative, then the reaction is spontaneous. Okay, and we can calculate that in few different ways. Same thing applies for equilibrium reactions. If the forward reaction, actually let's talk about that later. But still, if the Gibbs energy change is negative, then it means that the reaction is spontaneous. Okay, and now, so that we understand what happens in molecular level at a huge system at equilibrium, let's now first consider a really simple example. Okay, so on this slide and in the next slide, we have some kind of reaction where we have gaseous reactant and gaseous product. Okay, and for this reaction, the enthalpy change is 0, entropy change is 0, so the Gibbs energy change is going to be 0. Okay. So now, if we take a look at the reaction, and let's see what happens to the entropy when the reaction starts going on. So in the y-axis we have reaction quotient, in the y-axis we have entropy. So in the beginning we have only reactants there. So the reaction quotient is 0. And what on earth was reaction quotient? It was basically equilibrium constant, but reaction quotient is at certain time. It might be exactly the equilibrium constant, or it might be bigger, it might be less. But it is concentration of the products. Oh god, this looks horrible. Divided by concentration of the reactants. Yeah. So in the beginning, we have only reactants. Product, the amount of products is 0, so we get 0 out from this. And then what starts to happen is that the reaction starts going and going and going, and at some point in this reaction we reach the maximum entropy. Then according to the second law of thermodynamics, this is the sweet spot. This is how long the reaction is spontaneous. So the entropy is its largest at that moment. So when the Q is 1 in our fancy imaginary reaction. Okay. And if we keep on going so that we get more and more products, the R gets smaller, this gets greater, and the Q increases. Okay, so the entropy is its greatest when we have reactants and products in the mixture. Alrighty. So now if we take a look at the change in Gibbs energy in general, what happens when now we are still using this same imaginary reaction. We have reactant, we have products. Oh god, that looks horrible. No, I can't get rid of it. But still, reactant, we get product out from it. So now in this graph, we have again the reaction quotient here in the x-axis, but now on the y-axis we have the total Gibbs energy of the reactants and products. So if when we start the reaction, the amount of products is 0, so the Q is again 0. And at that time, the Gibbs energy is really high. But now when the reaction keeps on going, when we reach the equilibrium mixture, the point at which the entropy is at its greatest, then also the Gibbs energy reaches the minimum value. So the reaction is spontaneous when we start going from pure reactants to pure, equilibrium mixture, or from pure products to equilibrium mixture. So actually here should be equilibrium arrow here. Alrighty. So when we start from any part from pure reactants or pure products, depending on what is the Gibbs energy value of the reactants and products, the reaction might be spontaneously going towards equilibrium. If that minimizes the Gibbs energy change, then that is spontaneous. Alrighty. And at the sweet spot, the Gibbs energy change is 0, and then the reaction is at its equilibrium. So if the Gibbs energy change is positive, then it means that we have more products than reactants, since the energy change is, products minus reactants, and therefore the reaction will start proceeding in the backward direction. Let's see more general example of this, what happens to the Gibbs energy changes and when the reaction is spontaneous and not. This graph here should give you nightmares, because it gives nightmares to me also. This is not the most, but we will live with this. So now let's consider in general equilibrium reaction. We have here reactants and we have here products. Alright. So now let's consider a situation where in this equilibrium the Gibbs energy of the reactants is greater than the Gibbs energy of the products. And in this hideous graph here, on the y-axis we have total free energy of reactants and products. So total free Gibbs energy. And since now in this assumption the Gibbs energy of reactants is greater than Gibbs energy of products, the curve will look like this, whatever this is. On the y-axis here is Gibbs energy of reactants. On the y-axis here we have Gibbs energy of the products. And notice that still the Gibbs energy is Gibbs energy of products minus Gibbs energy of the reactants when we calculate the Gibbs energy change. Alright. Let's assume that we have only reactants in the beginning. So we have only reactants here, lots of them. Pure reactants in the x-axis, it tells us well, how much we have reactants, how much we have products. Alrighty. So what will start to happen? Well, the Gibbs energy is really, really big. The total Gibbs energy, it equals to the Gibbs energy of the reactants. And what nature does? Nature wants to minimize the Gibbs energy change. So the reaction will start shifting to the right. So this is the direction in which the reaction will start going spontaneously. And this will keep on going until we find a sweet spot at which, when we calculate the Gibbs energy change, products minus reactants, when this value here is at its greatest, then the reaction stops being spontaneous when going from pure reactants towards the pure products. Here we have the minimum Gibbs energy for that system. Here the entropy is at its greatest, and so on. It might be confusing, like, why on earth do we need to use this kind of graph to understand that, okay, the nature tends to minimize the Gibbs energy change? Well, IB likes to use this graph, so that is the reason. Not my favorite graph, but we will use it. Alrighty. Yeah, like that. So now when we take a look at the equilibrium mixture, in cases like this, when the Gibbs energy of the reactants is much greater than the Gibbs energy of the products, and we let the reaction proceed towards the equilibrium, in the end, at equilibrium, there should be, in that equilibrium mixture, most of the substances are reactants. I'm sorry, no. High concentration of products. So most of the substances are products there. Because if the Gibbs energy of the products is smaller than the Gibbs energy of the reactants, of course we will be closer on that end. So there will be more products in the equilibrium. Alrighty. Let's see a case if we have the, well, same case that the Gibbs energy of the reactants is greater than the Gibbs energy of the products. But now let's assume that we have only products in the beginning. Again, the Gibbs energy is greater than what it could be. We have only products, so the reverse reaction will start happening more quickly for a moment. The equilibrium shifts to the left, and the Gibbs energy change in total will start getting smaller and smaller. This will be a spontaneous reaction until we have found that sweet spot. And again, if we take a look at the ratio, how much we have products, how much we have reactants, well, the amount of products should be greater. Because, well, we are more on the right of this magnificent graph. Yay. Let's see another case. Because, well, it can be the way around. Either the Gibbs energy of the reactants is greater than the Gibbs energy of the products, or it might be another way around. Gibbs energy of the products is greater than Gibbs energy of the reactant. In which cases the, well, shifting left, shifting right will be spontaneous. When we have achieved the equilibrium, will there be greater ratio of products than reactants, or other way around? So just like before, well, if we start from a case where we have only reactants, the Gibbs energy is something, but when the equilibrium starts to form, that starts to form because, well, nature can minimize the Gibbs energy change, and this is again going to be a spontaneous reaction, and we find that sweet spot. And since, well, we started only from pure reactants, in the equilibrium there will be most of the substances pure reactants. So that is the case when we start with when we start in a situation where we have greater Gibbs energy of the products than greater Gibbs energy of the reactants. You don't need to be, well, a doctor to understand that if we start from the right end in this curve, so what will then happen? Okay, there is now typo. This should be products. So if we start from here, the Gibbs energy is enormous. We can minimize it by going towards reactants. Equilibrium shifts toward reactants. We find the sweet spot. And again, there is high concentration of reactants, small concentration of products, because, well, the reactants, they have smaller Gibbs energy overall. So, really difficult thing, really difficult graphs. What on earth is happening? Just remember that you need to be able to find that sweet spot. You need to understand that it is equilibrium, and at that equilibrium the Gibbs energy change is, well, minimized. And also that when we are going towards that sweet spot, in those cases the Gibbs energy change is negative. And they are spontaneous. Alrighty, let's see, well, something, well, more easy. So that was molecular level, or how can I say, more theoretical viewpoint, how equilibrium and Gibbs energy are connected. But can we calculate something with it? Yes, we can. So you are given this formula. It is not derived in IB. It will be derived in university when you all go there and start studying physical chemistry. So if we know for an equilibrium reaction, if we know what is the equilibrium constant, we can find out what is the Gibbs energy change with this formula. So minus RT ln K, where the R is the molar gas constant, T is the temperature in kelvins. So this is how we do it. And now with those values that we get out from here, we can predict how much there is stuff in the, well, final equilibrium. What is the ratio of the products to reactants? So if you take a look at this formula, the K was the ratio of the products and reactants. There was concentrations, multiplication, stuff like that. But if the amount of products is greater than reactants, and you get greater number than 1, then this ln term will be greater than 0. Then this will be greater than 0, and there will be minus sign, so it will be negative, the Gibbs energy change. So that was the case 1. We have mainly products, K will be greater than 1, the ln K will be positive, and the Gibbs energy change will be negative. So with this formula, with the results that we get out from it, we can, well, calculate what is the value of K, and with that we can state, is there mainly products or mainly reactants, or is there appreciable amounts of both reactants and products, like that. The values that we get out from here, the unit is again kilojoules per mole. Well, what does it tell us? Here is a nice table that tells you, well, a little bit about the ratios. So if the Gibbs energy change is 0 for equilibrium reaction, and then in that case the K is 1. So there is not always, but there can be same amount of products and reactants. If the Gibbs energy is greater than 0, smaller than 30 kilojoules per mole, hold on, well then the K is going to be smaller than 0, because ln K when it's smaller than 0 is minus, and you have minus RT times ln something, and you get positive number, and these are positive numbers. But if the value that you get is greater than 30 kilojoules per mole, then it means that it is, well, favoring the reactant side so much that, well, the spontaneous change is impossible, no reaction. So the reaction is actually not going towards products at all, spontaneously. When you don't have anything better to do, you can test with some values. What do you get out from the formula? Again, I don't recommend that you try to memorize this table. It is nice. It might give you some hints where the equilibrium lays, but still, maybe try some values here and see what kind of values get out from there. I think you got it. Okay, let's see an example calculation. Equilibrium reaction that produces water between protons and hydroxide ions has Gibbs free energy change of minus 79,900 joules per mole. What is the equilibrium constant for this reaction? Assume standard conditions. I'm not supposed to give my opinion, but maybe pause, maybe try to calculate this on your own first. Alrighty, so equilibrium reaction that produces water between protons and hydroxide ions. Well, protons reacting with hydroxide ions forming water. So that kind of equilibrium reaction has Gibbs free energy change of minus 79,900. When we take the formula, of course, well, we recognize that only way to connect the Gibbs energy and the equilibrium constant K in this is this formula. We have no other way to do it. We know G, we know R, we know... Hold on, it says standard conditions. We even know T. So the only thing that we have to solve is K from this equation. So this is math problem basically. You have to solve K from this equation. How to do it? Well, what I do is that I first divide with minus RT. It is positive number, no need to be worried if we break something. So ln K is this hideous thing over here. Then we need to get rid of the ln part there. What we can do is that we can raise everything to the power of e. And if you didn't know, e to the power of ln something is something. So that is how we get rid of the k. And the answer is e to the power of minus Gibbs energy change divided by RT. So now we just place their numbers and hope that we get something that is reasonable. K is e to the power of, it was minus, so 79,900 divided by 8.322, e to the power of 32, and we get 9.87 times 10 to the power of 15. So what does that mean? the equilibrium constant for that reaction is really huge. So it means that there's mainly products. And that should be the case. When you have water at room temperature, it is mostly water. There is a small number of protons and hydroxide ions. That was the ionic product of water. Also, in the last slide, this Gibbs energy is way smaller than 30 kilojoules per mole, so it means that we have mainly products here. Okay, what else funny we can find out from the equilibrium? Well, this is side quest. How is the equilibrium constant connected to the rate constant? It works now only with this example that I'm going to go through. So let's say an example of rusting. Rusting of iron is long and complex process starting with the iron reacting with oxygen and we get iron oxide. The equilibrium constant is enormous, but that reaction is really slow. So what is the connection between rate constant K and equilibrium constant K? Is there some kind of connection? So let's consider in general. Let's consider equilibrium reaction A plus B, equilibrium C plus D. And let's assume that the rate for the forward reaction is K times concentration of A times concentration of B. And let's assume that the rate for the reverse reaction is K, comma, times concentration of C times concentration of D. Okay. So this comes from the reaction kinetics. If we write the equilibrium constant for that reaction, it is products here, reactants here, their concentrations multiplied by one another. At equilibrium, the rate of the forward reaction should equal the rate of the reverse reaction. So that means that the KAB equals K, CD, because these equal at equilibrium. So let's divide with K, and let's divide with AB, because why not? Trust me. Hold my hand. So we get K divided by K, and we get CD divided by AB. And, oh boy, this fellow here is actually the equilibrium constant. So we can replace that with K, and we get this result, which now works only for this my example here. But we can use it to generalize the results. And what is the connection between equilibrium constant and rate constants? So equilibrium constant is a rate constant of the forward reaction divided by the rate constant of the reverse reaction. This is actually a pretty useful tool. So if this works well in both ways, if we mathematically think about this, if the K is really big, the K, well, it also, if the K is greater than K, well, then we are getting huge equilibrium constant values. What does that mean? It means that, well, the equilibrium lies on the right. So there is mostly products, a little bit of reactants. So if the rate constant K is much greater than the rate constant of the reverse reaction, then the equilibrium constant is large, to put it another way around. If it goes another way around, so that the reverse reactions rate constant is much greater than rate constant of the forward reaction, then it means that the reaction barely takes a place. And in that case, the value for the K is going to be really small, smaller than 1. And, well, we get small values for this equation if and only if the amount of C and D is small and the amount of A and B is big. Alrighty. Your book has some nice, well, tips, hints, tricks where to apply this knowledge. I highly recommend that you take a look at it. Just try to remember that when we add catalyst in any equilibrium reaction, well, the amount of K and K comma are increased as much. So the equilibrium constant in the end is not affected. Equilibrium constant depends only on the temperature. Now you can work with exercises. Have a really nice working time.